Hello, everybody. Today we'll be going over the first chapter in our AP Chemistry curriculum. Um, we have about 20 chapters to go to cover the entire course. Each of these videos is designed to be about 45 minutes to an hour, and it will summarize the chapter for you kind of before you get to class. So think of it as an alternative to like reading a textbook to kind of understand things before the class. You'll be watching the video and filling out the guided notes packets that I give you in class. If you do not have the guided notes packets, they can be found on Schoology under the exactly where you found the link to this video as well. Okay. Because this is the first video, how I would like you to take notes on this video. If you look at your packet, there's lots of blanks. And as I pull up the PowerPoint here I have the first slide, but as you go on to the ones with content on them, I have some different colored words. This time they're red. That correspond to where your blanks are to try to speed it up for you so you're not just spending a lot of time listening or re-listening to slides trying to write in all the words. Okay. The goal is just for you to write down a couple things. Main thing I want you to be doing is just watching the video. So if you need to pause at any time or rewind, that's definitely an option. Some slides I probably won't give you enough time to write everything down. So definitely take advantage of pausing. Even if you want to write everything, pause, write everything, and then listen to me talk about it. I will be spending a couple minutes on each slide as we go through. This PowerPoint is 33, just so you know, so that's about average. It'll be full of lots of information like this, which you just fill in the missing words, but it also will have, let's find one, different examples. On your worksheets, I've left you areas in the examples. I left you room to write down and copy whatever I do up here. So this first unit's a little bit weird, but usually these would be math problems or written explanations for problems. So here's an example of a couple examples we'll be doing later. These are some math ones, and I would like you to get your full points for the lesson, to fill in any of the blanks with the red words, and then any of the examples, also make sure you have all the work for those as well. And we'll be working through all of that together with the goal of having all of this complete whenever I tell you it's due. Okay? So, again, this is not all stuff I expect you to know, of course. This is introducing new material to you. So if you have questions about any of the examples and stuff, make sure to write them down. You can come to me before or after class. We can talk about them, or these would be great questions to ask in those first couple days we go over this content in class. So I would recommend another thing maybe to have is like a highlighter or something. So if you had a question about a section that you don't think I covered very well, or you have questions about an example, definitely star that for yourself so you can ask, good questions. And that's kind of the point of this, is so that you're ready for class. And this does constitute most of your homework, so I do expect you to engage with the video, and I do expect you to have everything completed in whatever I ask you to have it do. Okay? So this one is chapter 1, and now this one's a bit of a unique chapter. It's kind of an introduction. This one is the only one we're going to do this year that doesn't directly correlate to your curriculum. This is all kind of just like introduction stuff that's not AP Chemistry specific. These things we're going to talk about in here are really just to build some foundational skills that we're going to need going forward, hence the title. Okay, so let's go ahead and jump in and get started with that. We'll be talking today about the scientific method a little bit, not going into detail, but just kind of in general. Measurement, how to properly measure in the lab. Temperature, different scales of temperature, density, and classification of matter. So mostly things that you definitely have heard about before. All right. We're going to start with atoms and molecules, just a little bit of vocabulary. We've learned in honors chemistry or previous science classes that matter means just all the different stuff in the universe that has mass and takes up space is made of these tiny particles called atoms. And atoms are the smallest fundamental particle, meaning it's the smallest part of something that still retains the properties of that element. So I can have one atom of gold. I cannot have any less than that. If I split that atom apart, I would be splitting it into its subatomic particles. So those wouldn't actually be gold anymore. So it's the smallest fundamental particle of all stuff. Okay? A molecule is two or more atoms that you've joined together. They act as a unit and have completely new properties to the individual atoms that compose them. Chemical reactions, we're going to learn plenty more about. Unit 4 this year is actually all about chemical reactions, but We will obviously need them a little bit before, so that's why I'm going to give you some information here. So one substance changes to another by reorganizing the way atoms are attached to each other. That's called a chemical reaction or a chemical change. You're starting on the left side of a reaction, our reactant side, right, with two different substances, two different molecules here, and you end, and the things are still the same. You still have the same number of C's, H's, and O's, but them being ordered differently changes their properties drastically. CO2 and H2O are, in this reaction, they'd be gases, and I'm starting with a gas and then some methane. So like these are completely different substances just by how they're reorganized. And that's the basis of chemistry. We're going to briefly talk about a couple of the important laws that we kind of take for granted. These are things that in honors chemistry we learn, but we don't need to learn the laws themselves. But these kind of form the foundations for what we're talking about with atoms and molecules in chemical reactions. So the first law that you may have heard before is the law of conservation of mass, saying mass is not created or destroyed. It can only be transformed from one type to another. Okay? What does that actually mean? It means during a chemical reaction or any other type of change, the total amount of mass before and after must be the same. So in that reaction we were just looking at here, if I start with a total mass over here of 50 grams, I'm going to end with exactly 50 grams if I'm able to account for absolutely everything. Okay? You cannot create or destroy matter. Another way to think about that is that the total amount of matter in the entire universe is constant, which is pretty much more or less true. All right, our next important law is called the law of definite proportion. A given compound, so a compound is another name for a molecule, multiple atoms joined together, two or more, always contain exactly the same proportion of elements by mass. Okay, that's more difficult wording than it needs to be. What this actually means is a chemical compound like H2O always contains the exact ratio of 2 H's and 1 O, which makes sense. Since hydrogen weighs 1 and hydrogen weighs 16, a sample of H2O will always contain 11.1%, 2 out of 18 of those mass units of hydrogen, and 88.9% oxygen. Okay? Basically, this is just saying chemical formulas are a thing, and they are the exact ratios of elements that you find in compounds. Another way to kind of think about this is you're never going to have like half of an atom or anything like that, right? You're not going to have an unequal amount of, it's always going to obey the chemical formula. Okay, and the next law goes into that as well, the law of multiple proportions. When two elements form a series of compounds, okay, so multiple compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. And again, that's a super annoying mess to read through. But that just means you can only have whole numbers in chemical formulas. Okay, this says C.5H6 cannot exist. This makes sense, right? We know you can't have half of an atom, but these are just the laws that kind of support our ideas. Okay. All right, so here is a small table of the fundamental SI units. So these are all the different units we'll be using throughout the year, their full names and their abbreviations. Okay? It's definitely important to know all of these. The SI unit for mass being a kilogram is one that might be weird because we always will use grams, but the SI unit is technically the kilogram. If you take a physics class, you'll use kilograms all the time because physics is about big stuff like trains moving and stuff. You want to measure it in kilograms. Chemistry, we always use grams. Chemistry is about small little things like tiny little compounds and stuff. So we use the smaller unit grams. But all these other units we'll be using throughout the year. Meters, seconds, Kelvin, amperes, and moles. Okay. Mass is the amount of matter in an object. Mass, it will almost always be measured in grams, like I was saying in chemistry. Grams are small. Chemistry is about small things. Weight is actually not quite the same thing as mass, even though in 99.9% of cases it will be. Weight, the technical definition, is the measure of the force of gravity acting on an object's mass. So think about it. Your weight here on Earth is pretty much constant because we're always under Earth's gravity. But it would make sense that you weigh less on the moon. There's less gravity on the moon. You're not being pulled down, so you feel lightweight. And that would be true. You'd be much lighter on the moon. You'd be slightly lighter on Mars because there's less gravity on these different places. So weight isn't a very good unit of measuring how much something is, or how much of something you have, right? The amount of matter. Mass is a lot better, but when we do chemistry, we're always doing it on Earth, so it doesn't really matter. You'll see the words used interchangeably, but almost always on like the AP exam and stuff, we're going to talk about mass. Volume is another important concept you should know. Volume is the amount of space that an object takes up, that some matter takes up. You can have solids, liquids, and gases all have volume in kind of their own different ways. The volume of a solid is usually measured in one of these units, in a cubic centimeter or a cubic meter. You might hear that when you're learning, if you like, your house has like a cubic meter volume that it takes up or something. It's kind of like the square footage, but essentially the same, right? Or the cubic meters of like a tiny little object, you can measure it. For that sort of volume, you'd be using the traditional length times width times height formula. Okay, so that's how you take the measurement of a volume of a solid, is just length times width times height. A volume of a liquid is measured in liters or milliliters. We don't use any of the other like English units. We don't use cups or anything like that, or ounces. We use liters or milliliters. Liquids are the easiest things to measure their volume of. You use a graduated cylinder and other piece of analytical volumetric equipment like that to measure something's volume. You can actually convert between solid and liquid volume by using the relationship below. 1 milliliter is actually the exact same amount as 1 cubic centimeter. So if you have the cubic centimeters of a solid, you can convert that into volume of a liquid and back and forth. We'll learn about the volume of gases later, but gases don't really have a volume in the traditional sense. They just kind of expand to fill up their container, whatever that container is. So we just say the volume of the container is also the volume of the gas. But it's just the amount of space something's taking up. All right, so first topic here is using a burette or a graduated cylinder to measure volume. So this actually is a very common question on the AP exam, is literally just reading the graduated cylinder or reading the piece of equipment correctly. So first of all, the volume is always read at the bottom of this little curve, okay? Due to cohesion and adhesion, that stuff you learn in biology, the water molecules near the sides of this glass will like to stick to it, right? And they'll kind of be adhered to the side of this container. But the ones in the middle don't have like a piece of glass to be stuck to. So you'll actually see this slight little curve. And you can see if you look over here how drastic it is. It changes by like almost 2 or 0.2 milliliters. Okay. Always read from the bottom of that curve called a meniscus. When we measure something, we're going to measure what we call all of these certain digits. So if we look at our tool here, okay, we have markings on the right side here. I can tell that this meniscus, the bottom of this, I have this little black line you might be able to see here, kind of denoting where I think it is. Okay, it's definitely, I have markings to tell me it's between 5 and 6 for sure. I am certain about that. Okay, I can also read these little markings on here, right? So I have some markings here, some markings here and here. I think it's definitely between these two. Right? And there's not really an argument that could be made. You know, maybe our eyes are slightly different, but these markings on the instrument tell us that our reading should definitely be between those two lines. Those are all certain digits. I'm actually using the hash marks on my device to be able to make that volume measurement. Okay. When we measure properly in the lab, we're going to record all of those certain digits. So some instruments have a lot, some will have a few. Okay. And then also we're going to make one estimate. One estimated final digit called an uncertain digit. Okay, I don't have any more hash marks to use, but I can kind of estimate, right, that this is like, I'd say like maybe 30% of the way in between these two lines. You might get a different number. You might say 40% or 20%, right? We can't exactly say for sure, so we call it an uncertain digit. Now, when I'm measuring this, when I record my measurement, I'm going to record 5.1 something. We should all have the same 5.1 though. And I would guess 5.13. You might guess 5.14, or that last digit's allowed to be different. That's our uncertain digit that's up to the person reading. We all might see that differently, but those first two digits should always be the same. It's very important when you make any sort of measurement using a graduated cylinder or a ruler or a thermometer to do that, to record every single certain digit plus one uncertain one. Okay, so this is kind of going over the same idea again, right? So you can copy in right here. For example, the volume here is 5.1 something. The graduated cylinder tells us its volume is between 5.1 and 5.2 for sure. I estimate the volume here to be, well, I lied. Apparently when I made this PowerPoint, I said 5.18. That last digit's not really that important though, okay? Your last digit might be different. This is a way to apply the concept of significant figures in the laboratory, making sure that when you make a measurement, you're using the correct amount of precision. I couldn't say that this measurement's any more precise than that. I would be lying. I'd be adding extra information that wasn't there. I couldn't tell you that this is exactly 5.1726 milliliters, right? My instrument is not precise enough to make that. I could get a more precise instrument and maybe be able to tell you that though. So here's our first example. We're going to go through a couple of these measuring ideas, and we have to keep in mind, record all the certain digits and one uncertain digit. 4 students attempted to record the volume of the liquid shown here. Which students' recorded volumes are acceptable, and why are the others incorrect? All right, so I'm keeping that in mind. I'm just going to go over it. I'm just going to try to read what I think this would be. So I have a different instrument this time, so each dash is 1 milliliter. So this is 24. I'm going to make sure to read from the bottom of the meniscus. So that looks like, to me, it's like right at 24. So when I record that, I would record 24 because that's what my instrument is telling me. So I'm going to record. You can't quite see. There we go. 24. And that's all my instrument is telling me, but I need to guess one more digit. Even if I think that digit is a 0, I need to include that. The 24.0 and 24 are not exactly the same number. I mean, they are mathematically the same number, but this is actually 10 times more precise. Okay. This one can much more easily be 23.6. That just got rounded up to 24. So I need to think about that when I'm looking at my question here. I have my 4 different measurements. Every single one should include the 24 if it's correct. This last digit, though, is kind of subject to change. So another example of a right answer would be 24.1. Maybe you thought that line was just above, right, the line. Or 23.9 would also be good. Okay? The idea is you need to have all the digits you're being told for certain plus 1 extra. So that means of these, student C is the one we agree with. He is correct. Student A and B are not using all of the precision available. Their answers are not precise enough. Student D is 23.99. We don't have the technology for that, right? We don't have the instrument for that. Okay? We could say 23.9 maybe, or 24.0, but 0.99 is far too precise for the information we actually have. I know it's kind of like annoying and very specific, but this literally shows up on the AP exam probably every other year. Here's a couple more examples here we want to try to properly read. I have a ruler on the left, we have a thermometer on the right. Let's try to use our idea. Now, depending on how our ruler looks and stuff like that, our precision is going to have more or less decimal places than our example before. So let's start by looking at the ruler over here. I'm just going to kind of talk about it. I don't need to write anything here. It kind of looks like it's right in between these two hash marks for me. So that'd be 10.2 over here, 10.3 over here. So it's definitely between those. Sorry, I said 10. 1.2, 1.3 here. So I'd say 1.2 and then make my guess of my next digit, 5. I would say this left one is 1.25. If you just said 1.2 or 1.3, it would actually be wrong. If you said 1.235 or you're adding in more digits, it would be wrong, right? Use all the digits on the instrument plus one more. On the right here, so I have my thermometer. It doesn't give me Celsius or Fahrenheit. It doesn't really matter. Let's just assume it's Celsius. So here we're counting by 2s. So we have 72, 74, 76, almost up to 78. I think it's just below it. So what I would say here, this is 76 or 77. It's not quite 78. So I would say this is like 77 points, and then I have to make my one guess. So I could say 77.8, something like that. 77.9, right? The idea is I need that one uncertain digit as my guess, my estimation of what it is. Okay. Next topic, we have precision and accuracy. Some vocabulary that might potentially come up throughout our labs and stuff like that. So accuracy, when you're doing some sort of scientific investigation, is how close your measurement is to the true value. So maybe you're trying to determine experimentally the molar mass of sugar. The accuracy would be how close you are to the actual accepted value. So if you got within like 1% or something, that'd be a very accurate measurement. You have good accuracy if your recorded value is really close to being correct. Now, precision's not quite the same thing, even though in like our day-to-day speaking, we might use the two pretty much meaning the same thing. Precision is when you have multiple measurements, how close they are together. How close all your trials are to each other. Not how close they are to the actual result, but just how precise they are, meaning how close are they to each other. You have good precision if each of your trials are really close to each other. Okay, the actual molar mass of sugar is around 180 grams per mole. A measurement like 179 would be accurate. Say you tried to find the molar mass 6 times and every time you got 45 grams per mole. Nowhere near the right answer. But if all your measurements were really close to each other, that means you at least had a lot of precision. Right? Whatever you were doing it correctly over and over. You just might have had a fault somewhere in your procedure, or might not be thinking about everything. Okay? All right, some more kind of introduction stuff. Here are different prefixes that are used in the SI system. I'm sure you're familiar with a lot of these. There are some really, really tiny ones at the bottom. The only ones I really care, the ones we might ever use, are the ones in red there. Nano, micro, milli, centi. We use a lot of these really small ones because, again, we deal with a lot of really small stuff in chemistry. Kilo, that one's pretty common, kilometer and stuff like that. And then mega you might see for like megahertz or something later, but these are the main ones that you definitely would use. There are a couple things that go super, super small that I might talk about, like a picometer or something like that, when we're describing like how far away atoms are from each other or something like that. But we don't really use those very often. These are the ones you definitely should know. All right. I have both the meaning here with a regular number and the exponent. Hopefully we feel a little bit comfortable with exponents. We use scientific notation constantly in this class. So you should know that these numbers are like equivalent to each other. Remember that if you're not exactly sure how to switch between them, a negative exponent just means you would go where your decimal starts. So for this 10 to the negative second, it would be at the end, right? And you just move it that many times to the left. More or less. We'll go over that more a little bit. All right. Yeah. We're going to use that for our examples coming up here. So our dimensional analysis. So unit conversions are everywhere in chemistry. We're constantly converting in the lab, doing all sorts of different measurements, doing stoichiometry. So hopefully stuff you remember a good bit from honors chemistry. It does not go away in this class at all. If you had me before, you know I like to use what I call the train track method. If you look at this picture in the middle here, that is what I call a train track. It's a way to organize our unit conversions into one sort of concise problem. Okay? I think this works the best. And so because of that, this is the one I'll be using constantly. But if you have a slightly different method you use for like a dimensional analysis or a unit conversion problem, that's okay. But it is very important that you show your work. For my class, just to like make sure I know what you're doing, but also for the AP exam. As we're going to go over the FRQ section, that you will not be able to get all points for everything unless you show your work. There are certain questions where even if you put the perfect answer, if you did all the calculation in your calculator, but you didn't show your work, you lose points or you lose half the points. So it's vital you show your work, even on something like a train track problem like this. All right. So we're going to go through several examples. Review for people who had me before. If you aren't exactly comfortable with this sort of thing, we're definitely doing these a lot in class as well. The idea is we have this train track, which kind of functions as a big fraction. All the numbers on top here are things we're going to multiply together. They're like the top of a big fraction. All of the things on bottom are the bottom of our fraction. So this conversion here, what it's going from, it wants to convert 2.5 days into seconds. I'm going to see how many seconds are in 2.5 days. How you're going to make this work is you're going to take whatever number I give you that you want to convert, whatever you're starting with, put it in the top left box. Then what you're going to do is take that unit, and we need to get rid of that unit. We need to cancel it out. I don't want to know about days anymore. So I'm going to take days and put it on the bottom of my next line. You have the same thing on top and bottom of a fraction bar. They cancel. You're going to put the new unit you want to find on top, and that'll be your new unit. And then we're going to kind of make a chain where we just keep doing that same thing over and over. I have hours. I don't want hours anymore. I'm going to cancel it. Put hour on the next line on the bottom, so those two units cancel. Put the next unit I can find on top, and so on. So in this one, to go from 2.5 days into seconds, I've used 3 separate steps here, 3 unit conversions. So I put days on the bottom. I know how many hours are in one day. So I put 24 hours in one day. Okay, so on the next step, I'm going to get rid of hours by canceling hours. I don't know exactly how many seconds are in an hour off the top of my head, but I can tell you that there are 60 minutes. So I'd put 60 minutes on top over 1 hour because there's 60 minutes in 1 hour. Minutes is my unit on top. Cancel it by putting it on the bottom. I want seconds. So I know how many seconds are in a minute. So 60 seconds in 1 minute. So the train tracks like that just help you organize all your different conversions into one problem. And then once you get to the end, what you're going to do, all the numbers you end up with on top, multiply them. So 2.5 times 24 times 60 times 60. Any number on bottom, you divide by it. So you divide by 1, divide by 1, divide by 1. And you get your answer. Okay. So I have a handful of examples we're going to go through. Some of them are with unit conversions like this, and then some of them get a little bit more complicated. So I want to convert 25 kilometers. So that's what I'm starting with. 25 kilometers. And I want to convert it into nanometers. All right, I'm going to draw my train track. This is the number I have, so I'm going to put 25 in its unit, kilometers, in the top left. And I eventually want to get to nanometers. Now, in my head, I don't know exactly how many nanometers in a kilometer or vice versa, but what I can do is kind of break this up into steps that I know. So like kilometers, I know I could turn kilometers into meters. We just saw on the previous slide, 1,000 meters equals 1 kilometer. Okay, so that helps me. And then once I have meters, I'll be able to think about that and convert it into nanometers. So that's on that previous slide. If you haven't used nanometers before, right, it's a million and 3 more. Sorry, it's a billion nanometers. Makes up 1 meter. Because a million is micro, a billion is nano. So, or you could do 1 times 10 to the 9th. That means the same thing, right? So either one you want to use there, if you don't want to write all the zeros. So I don't have this direct conversion. I'm sure you could figure it out, but I don't have it with my information. So just to practice, I'm going to leave it like this. I want to get from kilometers to nanometers. Kilometers is my unit on top. Let's get rid of that, putting it on the bottom. That'll make those units cancel. Okay. Meters is what I know how to go to, so I'll put that on top. And as we just stated up here, there's 1,000 meters and every 1 kilometer. So those would be the numbers I fill into that part of my dimensional analysis. I'll draw another line and continue. Meters is the unit I have now. Let's put meters on bottom so that it cancels. I want to find nanometers. I'll put that on top. Leave myself some room. Okay, we just talked about 1 meter being a billion nanometers. So I'm just going to put 1 times 10 to the 9th. Right? You could also put in that whole number there. And now we have the unit we want. Meters are gone. The only unit we're left with is the one we want. So that means we're ready to solve. Multiply all these numbers on top together. Okay, so I'm going to do, 25 times 1,000 times 1 times 10 to the 9th. I should have my scientific calculator, but I can type that on my phone. 1EE9 equals, and I get that whole number. That's a really long number, so I'm going to put it in scientific notation. 2.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th. Does that answer kind of make sense? Well, nanometers are really, really tiny. Kilometers are pretty big. So if I have 25 kilometers, it makes sense that'd be a whole bunch of nanometers. So that's a really big number. That sounds good in my head. All right, and that's our process. It's important to practice this. We're going to use this throughout the entire year. Next problem. So another example here. I'm going to convert 900 centimeters cubed into liters. All right, so these are both units of volume. I mentioned earlier that the way to convert from, this would be solid volume over here, because you're using like a ruler to measure centimeters. This is liquid volume, a liter. So we talked about 1 cubic centimeter is equal to 1 milliliter. So that's how those two things are related. Now that doesn't get me exactly to liters, but once I have milliliters, there's 1,000 milliliters in every 1 liter. So using those two conversions, I can kind of do the same thing with my train tracks to get to my answer. I'm going to start my 900 cubic centimeters. Go there. Cubic centimeter, I'm going to put it on bottom to cancel out. The unit I can turn this into that's useful to me is milliliters. So I'm going to put milliliters on top. Okay, our numbers here state 1 cubic centimeter equals 1 milliliter. So I'll put a 1 for each one. The math answer hasn't changed. That just kind of helps me set up my units correctly. I have milliliters. Milliliters need to cancel. I put them on the bottom. I'm looking for liters. I can put that on top because I know a conversion between those two. 1 liter is 1,000 milliliters. Milliliters cancel out. Liters is what I was looking for, so that means I'm ready for my answer. Multiply all the numbers on top, so I have 900 times 1 times 1. Divide by the numbers on bottom, so divide by 1, divide by 1,000. I have 0.9 liters. Okay, one more example using some unit conversions here. A car is advertised as having a top speed of 52 meters per second. I don't really know how fast that is. I don't think of my life in meters per second. Seems like it'd be fast. Let's find out how fast it is in miles per hour. So it gave us a little bit of extra info here, which is useful because I wouldn't know that 1 kilometer equals 0.621 miles, but now I do. Okay, I am starting with 52 meters per second, and let's go to miles per hour. I'm going to use MI for mile, not just M, because M is meters, and that'd be confusing, right? Okay, so I'm going to need a train track. I have to think about converting my numerator number here, right? My meters to miles, and my seconds into hours. Okay, so we haven't done one like this yet, but that's kind of another benefit of this train track method. What I'm going to do is I'm going to put in my 52 meters per second, but I'm just going to put meters on the top, and this, remember, is just like a division bar. So I'm going to put seconds on the bottom. So this is 52 meters per second, and that'll help me keep everything kind of situated right. I'm going to convert meters into miles first, or I could do the other one first, seconds into hours. Seconds into hours should be easy. We'll just go seconds into minutes, then into hours. Meters to miles, I might not know how to do, but I have this extra information here. So I can turn meters into kilometers, right, using those numbers that we wrote down earlier. But then once I have kilometers, I can use this information to turn it into miles. So a lot going on here. The order you do it in is not important, but I like to always just start with whatever unit I have here. Let's just be very careful where we put stuff to make sure we get our answer right. So I'm going to start with the meters. Let's try to turn this into miles. Meters goes on bottom to cancel the meters that's on top. Let's put it into kilometers. 1 kilometer is 1,000 meters. Meters, cancel. Kilometers is not my final unit, so I'm going to put kilometers on the bottom to cancel. I'm looking for miles, put miles on top. And that's where I'm going to use this information. It told me 1 kilometer is 0.621 miles. Just making sure I'm putting the number on the matching part. The whole purpose of having the units here is so that it helps me put the numbers in the right spot. Because if I accidentally flip these, I'd get it wrong. Okay, if I think about where I am now, I know miles is my unit now, but I also have seconds. So this is miles per second. If I were to solve, I would get my answer in miles per second. Let's go ahead and just turn it into hours, though. Seconds is on bottom. To get rid of seconds, I'll have to put it on top. And I'm just going to go to my next open spot. Seconds, I'll convert into minutes. Seconds cancel. We know there are 60 seconds in 1 minute. I have miles per minute as my units. Let's turn in minutes into hours. Minutes cancel. 60 minutes, 1 hour. If you want to convert seconds straight into hours with 3,600, that's totally fine as well. All right, now we have a nice long expression here. We are ready to solve it. So all these numbers on top, I'm going to multiply them all together. 52 times, I'm going to skip the 1. I know it's not going to change anything. Times 60 again. Multiply it all together. Any number on the bottom, I'm going to divide by. The only number that matters is 1,000. So divide by 1,000. There's my answer. Okay, so my car is going 116 miles per hour. That makes a lot more sense to me. With rounding, we'll kind of go into this a little bit more together in class. There are specific ways you are supposed to round with significant figures, significant digits, if you've heard that before. We'll worry about that in class. But basically for now, let's just keep 3 digits. That's very safe. So keeping the first 3 not 0 numbers is usually going to be our best bet. So that's why I stopped at the 6. If you wrote more, that's fine. But if you'll get some non-repeating numbers. You're going to have to choose where to round eventually. So I usually just do 3 digits for a math problem. If I'm doing something in the lab where I'm trying to be really precise, I might use 5 or 6 digits though. Okay. All right. Next topic is density. Density is the mass of substance per unit volume. So it's how much stuff is stuffed into how much space. So things that are not dense feel very, very light, even if they're big. Like cotton candy is very low density. You can have a giant glob of cotton candy and it's not very heavy at all. Things like metals are very, very dense. Even if you have a tiny little ball of a dense metal, it'd be very, very heavy. Our common units we're going to use, most likely we're going to use this grams per milliliter. This got messed up a little bit. This should say density is mass divided by volume, of course. The line just moved a little bit. Kilograms per liter is another way to think about it. There's several units for density. It's basically any unit for mass divided by its volume. Solid objects have a density. Liquids have a density. Gases have a density too. Water has a density of exactly 1 gram per milliliter at 4 degrees Celsius. It actually changes a little bit depending on the temperature, but unless stated otherwise, water always has a density of 1. Meaning if you have 1,000 liters, it weighs 1,000 kilograms, which is really convenient. It lets you make measurements of the mass of volume of water really, really easily. Okay, here we have at 50 degrees Celsius, water has a density of 0.988. So it's actually a little bit less dense when it gets hotter. And if we kind of think about why, we'll learn more about this as we go through the year. The molecules are moving really, really fast, right? So they're probably like stretching out and like spacing themselves out a little bit more At 4 degrees Celsius, they'd be really cold, so they're not moving quite as much, so they might make more sense if they kind of clump together more on average. Okay, but water is actually really unique, so there's a lot going on there. Okay, so water has this density. How much does 2 liters of water weigh? So that means I'm looking for its mass. So let's density equals mass per volume. That's the easiest way to think about the formula for me. So I know my density is 0.988. I know my volume is 2 liters. So I'm just looking for my mass. All right, let's just solve. Solve for mass. 0.988 times 2. 1.976 is what I get. Again, I'm just going to round to the first 3 digits. So I'm going to say 1.98. I should know that this unit is kilograms because I used liters. Okay. If I said I have 2 milliliters of water, then this would have been 1.98 grams. Okay. Kilograms matches with liters. Milliliters matches with grams. Okay. Liters is kind of a big unit. Kilograms is kind of a big unit. They go together. Milliliters are tiny. Grams are tiny. They go together. A certain mineral has a mass of 17.8 grams and a volume of 2.35 centimeters cubed. What's the density of that substance? All right. A little more room. So, density again, always mass divided by volume. So, my mass here is 17.8 grams. My volume is 2.35 centimeters cubed. Now, I have a bunch of choices here. I could just solve this. My units would be grams per centimeters cubed. If the problem doesn't specify, that's totally fine. There's nothing wrong with that. I could also take centimeters cubed, turn them into milliliters. We just learned that that's just like a 1-to-1 ratio anyways. So I could also have my units be grams per milliliter. And that might be more comfortable, but they really mean the same thing. So for this one, it's a really easy problem. All I got to do is do my math. 17.8 divided by 2.35. Get a long number. Keep the first 3 non-zero digits. 7.57 grams per centimeter cubed. Okay. We're going to talk about measuring temperature. Temperature is the average energy of all particles in a system. Now, humans, we think about temperature in the way that's convenient to us. It's hot outside, right? If it's August, it's 100 degrees, right? That's useful to us. It tells us what I need to wear, how long I should be outside without water, or without shade, or without being able to go cool off, right? It's very useful to us to know the temperature, to know what to expect when we go outside, or into a room, or whatever. Temperature in science is a lot more complicated. We're going to talk about, we have a whole unit basically just on temperature called thermodynamics, learning about how heat moves. A lot of that has to do with temperature. So temperature is just how much energy the particles in the air have. When it's really, really hot outside, that just means the particles in the air are moving faster. They're bumping into you faster. They're applying more friction when they hit you and making you hotter. So that's all what a higher temperature means. It's just the stuff in the air is moving really, really fast because it has a lot of energy. So when the sun's really beating down on you, it's accelerating all the molecules in the atmosphere, all the nitrogen and all the oxygen. It's actually physically bumping into you harder, and that's why it feels hot. They're bumping into you more frequently. When it's cold outside, the opposite happens. The particles in the air have less average temperature. An air conditioner basically works like that. You're just trying to slow down or remove energy from all the air molecules. And when it does that, they're bumping into you less frequently with less force. Therefore, it feels colder. Most of what we feel with temperature is our brain tricking our body. Our brain knows about what environment we thrive best in, right? How much we need to sweat versus how warm we need to be for our functions to work. And will tell us there's too much air hitting me too hard, and that means it's hot. And for us, we know what it feels like when it's hot. Or the opposite, when it's cold, you start shivering. Your body has an actual response to that. All you need is for some particles to start hitting you faster. Now, most of the time, we'll use Celsius as our scale to measure temperature, but we also will use Kelvin a lot too. Kelvin is technically the SI unit when you need an absolute scale. Kelvin is useful because there are no negative Kelvin temperatures, which makes a lot of math a lot easier to solve. When we talk about gases, everything will be in Kelvin, right? So the reason being, scientists specifically made the scale so that 0 is the absolute lowest temperature you could ever have, absolute 0. Now, if we think about what absolute 0 means, temperature is the average energy in a gas or something like that, in a system. If at absolute 0, that would mean there's absolutely 0 energy, which is why it actually can't get colder than that. You can't give negative energy to a system, right? You can cool something down really, really close to absolute 0 by getting rid of all the little trace amounts of energy, but you can't make it have negative energy. If you make something move backwards, it's just moving forwards in a different direction. So it still has energy. Okay? So that's why you actually can't go below absolute 0, is because that is 0 energy at all. All right, to convert between the two scales, Celsius and Kelvin, the only ones we're going to use, you add or subtract 273. So to get to Kelvin, add 273. If you have Kelvin and for some reason you need to go back to Celsius, you subtract 273. The scales mean the same thing, they're just kind of shifted. If you increase the temperature by 1 degree Celsius, that's the exact same amount as increasing it by 1 degrees Kelvin. They just have a shift on the scale so that Kelvin, the lowest temperature, is 0. Okay? So negative 273 Celsius would be 0 Kelvin. All right, we're getting to the end here. We have mixtures. Mixtures are anything made of more than one thing. Homogeneous mixtures are the same throughout, meaning basically everything's kind of the same. Maybe not 100% perfectly random, but essentially imagine like a pancake, right? When you cook, we put all these different ingredients. You put an egg, you put flour, you put baking soda, whatever else you put in pancake. I don't know, sugar, I don't know. You mix all those things together, and when you cook it, the idea is you don't want lumps of sugar and lumps of egg and lumps. You want it to be spread out. So when you make your pancake, it's homogeneous. It tastes the same everywhere. Now, homogeneous or heterogeneous mixtures have uneven parts and are not the same everywhere, like a salad or something like that, right? You might want a piece of tomato and a piece of lettuce and some dressing and a piece of cheese or something. Now, in chemistry, we're going to talk about homogeneous mixtures way more. Okay? When we make solutions, that is our goal, is to make them homogeneous. I don't want to make an acid and the top part of it to be more acidic than the bottom, because then when I use a little bit of it, it's going to throw all my math off. We want everything we use to be homogeneous, right? So another name for homogeneous mixtures is a solution. All right, we're going to practice. Our first lab this year practices making mixtures in a couple different ways. Here are the tools that we're definitely going to need for that. On the left, this is a graduated cylinder. It's the easiest way to measure volume. In the middle, we have a scale, and we're measuring some little substance on there, and that little white plastic piece is called a weigh boat. Now, almost any time we measure something, we're going to use a weigh boat because you don't want to just pour this directly onto the scale. On the right is probably our most useful tool for making mixtures, for making solutions, is a volumetric flask. The volumetric flask works. You fill in the liquid all in this space here, and the only measurement you actually have is this little line. The little line is the exact amount you're always going to make. There's different flasks for different volumes. So this flask might be for 50 milliliters. And if you fill up to this line, it makes exactly 50 milliliters of solution. Or you might have a 100 milliliter flask or a 200 milliliter flask. Most of the time when we make solutions, we're going to use these because they're really convenient for holding and storing and mixing solutions. Okay, go over that in the lab for sure. All right, last little topic here is types of changes and some analytical techniques. So a physical change is a change in the form of a substance, but not in its chemical composition or properties. So it's just like changing what something physically looks like without actually changing what it is or what it does. For example, if you take water and you boil or you freeze it, right, you still have water. you still have H2O. You can unboil it, you can condense it, or you can unfreeze it, melt it, right? And you still have the same stuff. You dissolve something, right? If you take something, some salt, and you dissolve it into water, that makes a solution, and it might look like you can't get that back, but you could always just evaporate all the water away and you'd be left with your salt again. Okay? Changing the shape of something, changing the position of something, are all just physical changes that aren't actually changing the chemical composition. There's a couple ways we're going to take advantage of the different physical properties of something to separate it. The 3 techniques we're going to start with this year, and we're going to do all these later in their own labs kind of as we go through the year, are distillation, filtration, and chromatography. There's all different ways to separate something by its physical properties. Or chemical properties even. Okay. Distillations is the first one. Now, if you see movies where they're using chemistry equipment, this is a very common one to kind of show. How this works basically is you're going to take a couple liquids in here. Maybe you have, this is most commonly used in like making alcohols and stuff like that, right? For drinking or whatever. You have a mixture of liquids in this flask here, and you're going to heat it up. Well, all the different liquids boil at different temperatures. So we use alcohol a lot for this because alcohol boils really easily. If you have a mixture of, just say you have like a beer, right? Or any other drink like that, that's a mixture of water and ethanol, which is the alcohol in beer, okay? And you put it in this and you start to heat it up. The water isn't going to boil away right away. You're going to start heating it up and up and up, and you'll notice some stuff starts to boil, but the stuff that boils is the thing that boils the easiest, which is the alcohol. So you actually will boil out all the alcohol. It'll go up into this tube as a gas, and it'll start to go down this column as a gas, and what you're going to do is run really cold water through here. When the gas molecules come in contact with the cold water, they condense back into liquids, and actually will turn into liquids and start to drop down your distillation setup. So you take multiple liquids you want to separate by their boiling points, mix them in here, start heating them up. The liquids will start to boil in order of their boiling points, right? The one that's lowest, usually like an alcohol or something, will boil first. It'll turn into a gas, go up into this column. With the cold water here, will make it turn back into a liquid and condense away. It's a way to purify something. If you've heard of distilled water, this is essentially what that is. You're just taking a bunch of water and you are distilling it. You're heating it up until it all boils, leaving behind any impurities down here in this flask, letting it all boil, turn into a gas, condense back into a liquid, and you actually have a pure product at the end. Another example of a way to separate things is with filtration. So filtration is sometimes called gravity filtration or even gravimetric analysis. It's a way to separate solids from liquids. Okay, so here's a couple examples of pictures we have here. This one on the left uses a funnel, right, with some filter paper in it, like a coffee filter essentially, and you have a mixture here. Like you could use coffee as an example, or you can use anything else that has some solid mixed into a liquid. Right, as you pour it in here, all the solids are going to get caught by the filter paper and by the funnel, and all the liquids are going to be able to drip through. Okay. On the right here, this is a vacuum filtration pump. So this has a little vacuum that's going to apply a vacuum force to this tube, which is actually just going to help pull and suck the liquid down into the flask. Okay. So filtration, or gravity filtration, is a way just to separate solids and liquids. The third way to separate mixtures, is chromatography. There's a ton of different types of chromatography that are useful in different ways. What we're going to use in class is called paper chromatography. It separates samples out by their polarity. The polarity of something, it's basically just, does it have a positive end and a negative end? Molecules like water have a positive end and a negative end. If you're not sure about that or that you don't know why, we will go over that in detail later. But just different things have different what we call polarities, right? Now, what we're going to do with this is we have a piece of chromatography paper and some sort of solvent at the bottom of this container. So this is just 3D over here or 2D over here. It really is the same thing, okay? Well, this water is going to start through capillary action running up this paper. All right. So it starts to just soak up the paper slowly, and over the course of about 10 minutes or so, will fill and get most of the way up this paper. Well, this, whatever solvent you use down here, let's say we have water. It will dissolve some of the dyes or whatever other substance you have here. It'll actually drag them up the paper. Now, the more attracted your substance is to water, the more it's going to go up the paper. If it's not attracted to water or whatever else the solvent is, it's pretty much just going to stay in place and not really move. Now, we can see that over here on the right. Okay, so I had all my different samples here, and then some of them started to move up the paper, and like it looks like the yellow color moved the most, and then the green, and the red hardly moved at all. And this lets us separate out things by their polarities to see which thing is most polar, which thing is least polar. We're going to go over this in a lot more detail once we learn more about polarity, but for now we should know that it's a way to separate things by their polarity. Okay, so identify the type of separation you should use on the following sample. So this is going over the last 3 slides, so hopefully we remember. If I have sand mixed with water, okay, well, to get out the solid from the liquid, I'm going to use some sort of filter, right? I can either use vacuum filtration or just like drip through a coffee filter just to get the water out. So that'd be filtration. Next, polar and non-polar dyes are mixed in a sample of food coloring, right? Well, that's polar versus non-polar means they have different polarities, which means we'd have to use chromatography to separate them. Last, a glass of wine contains water and alcohol. Those are 2 different liquids. I can't just like filter out the alcohol. I'm going to have to do a distillation setup. Water and alcohol have different boiling points, so when I start to heat them both together, the alcohol will boil away much quicker than the water does. Right? And that'll let me separate them using distillation. All right, last topic here, we have 2 slides left, a chemical change. Now, the rest of the course is all about chemical changes. That's literally what chemistry and chemical reactions are. It's a substance turning into a new substance with new properties. A chemical change can only be undone by another chemical change. You can't reverse this. So our primary example is chemical reactions. When you have a chemical reaction, like this is the combustion of methane into carbon dioxide and water, you can't just undo that. This is fuel burning. You can't just like undo that, right? You can't just like, all right, I'm just going to smush the water and carbon dioxide back together and we'll just make more fuel. Now, hypothetically, you could have a chemical reaction where these 2 things react with a certain amount of energy to be able to produce this. But you need another chemical change to undo a chemical change. Other common examples of chemical changes are rusting, like a nail rusting. It turns iron into iron oxide. Digesting food is breaking chemical bonds to make simpler things our body can digest, like glucose. Burning is this example here, and lots of other chemical reactions. So we have a list here of 6. We want to identify them as physical or chemical changes. In the future, most of our examples will be doing math. This is kind of a weird unit, so this one you could just put physical or chemical next to these on your example. A little bit of a unique chapter here. So identify the following as physical or chemical changes. Burning firewood. You're burning something. That means you're actually combusting it, actually breaking apart chemical bonds to make new things. That is a chemical change. A nail rusting is a chemical change. A popsicle melts. Now you have popsicle or popsicle juice, and it's kind of the same thing. And if I wanted to, I could just refreeze the popsicle juice back into a popsicle. So that's a physical change. Nothing's actually changing there. I still have my combination of probably fruit juice and sugar and water, but it's just in a different form. Chopping apart firewood. Now I can't just like unchop it, but it's still firewood, right? It still has the same chemical composition, it's just a different shape. So that's a physical change as well. Shredding paper, taking paper and ripping it, that's kind of the exact same thing as chopping firewood. You still have paper, it's just a different size. Digesting food, like we said, breaking apart complex sugars into simple ones is a chemical change. All right at an hour, so that's good timing. Kind of our introduction chapter. Hopefully a lot of this is really, really familiar. Starting on the next chapter, we get to talk about more AP chemistry specific stuff. Okay, so make sure you have all those sets of notes filled out. Okay, but besides that, that's all I have for you today. Okay, everyone have a great day, and I will see you next time.